Let me do another example here. Let's see which one's the one I want to do next. Yeah, I'll do this one next. Okay, so let's do another example here. More business application example. Suppose for this problem. Suppose it tells us that a car dealership claims it can sell 12 cars per day on average. Now, suppose the manager of this dealership estimates that for each $300 price reduction, they can sell 2 more cars each day. All right, so they sell 12 cars per day on average, but then the manager believes that if they've reduced the price of their cars by $300, for each of these price reductions, they can sell 2 more cars each day. Now, what's going to be different from here is that X, unlike the other examples that we have done so far with business applications, X here is not going to stand for the number of cars. X in this case is going to stand for the number of price reductions. So X is going to represent the number of $300 price reductions. And what we want to do is first figure out what our price and quantity function is going to be in terms of what X is representing here. So price is going to depend on how many price reductions we're making, and the quantity will also depend on how many price reductions we have. Okay, oops, I forgot to mention something here. One more information. Car dealerships sell 12 cars per day on average at $15,000 a day. Or not $1,000 a day, $15,000 per car. Forgot to mention that part. We need to know the original price of the car. All right, so these cars that they're selling, they cost $15,000 each. At this price point, they sell 12 cars per day. But the manager believes that if we reduce this price by $300, for every time we reduce that price by $300, we can sell 2 more cars per day. All right. And if X stands for the number of price reductions, we want to figure out what our price and quantity needs to be. I kind of move the things a little bit here. Let's see if it just erases the highlight. Yeah. Let me just re-highlight some stuff here. All right, so 12 cars per day, $15,000 each. That's original amount of cars we can sell at that original price point. For each $100 price reduction, we can sell 2 more cars. And X is going to represent how many reductions we put on these cars. So let's figure out the price and quantity in terms of those number of price reductions. And if each car costs the company $12,000 to make, then what should be the quantity and price of these cars to maximize our profit? All right. So let's figure this out here. Let's see. Let's first determine what our price and quantity functions are going to be. Zoom, everything's good. Okay. So again, recall that section, the price function is known as little p of x. And our quantity function will be q of x, little q of x. Okay. Now, in this case, our price function, well, let's see. It tells us that originally, the original price of each car is $15,000. So we're gonna have $15,000 here. So 15,000. But we're trying to figure out what our price should be here if we want to maximize our profit. And to change the price, what we're going to be doing is see how many $300 price reductions we're going to have to apply. Again, the number of reductions are being represented by X here. Okay, how many reductions we're going to be making. So the price, the original price of the car is 50,000, but we're going to subtract this by 300 times X. All right, in other words, we're taking the original price minus the price per reduction. Then X represents how many times we're going to discount this car, and each discount is going to cost us 300 to reduce. Okay. But what about the quantity of the cars? Well, again, at the original price point of 50,000, we were able to produce and sell 12 cars per day. And then we believe that if we reduce our price by 300 bucks, each price reduction is going to result in us selling 2 more cars per day. So similar to what we have here, we're going to take our original amount, which is 12, plus 2 times X. In other words, the original quantity at the original price plus the quantity that we'll be able to sell per reduction. Okay. So 12 plus 2 times X. All right, so we've established our 2 functions here in terms of number of price reductions or price and quantity. And now we're going to figure out what should be the optimal price and quantity of cars that we're going to make and sell in order to maximize our profit. So we're going to find the price. So now using these 2 functions, we more want to try to find the price and quantity for maximum profit. Okay. Well, recall from what we have worked with before. How do we define profit again? As revenue minus cost. Right, our revenue minus our cost function. Do we have the revenue function or the cost function? Not yet. All we have is just the price and the quantity functions. So let's first figure out our revenue function, R of X. Okay, or let's rewrite this, do a little review. So recall from the previous section, from the last section that we did. In the last example that we did, 3.3, we did a little bit of maximizing, I believe, revenue. And recall the revenue is defined as price per unit. I'll use parentheses here. Price per unit multiply by quantity. In other words, to define R of X, what we're going to do here is multiply these 2 functions against one another. Price function times the quantity function. So P of X times Q of X. All right, so you're going to take our price function, which was 15,000 minus 300X, and then multiply this by 12 plus 2X. All right, so we got to fold this, so we have to FOIL this out. Foiling this out is going to give us, let's see, 180 times 12, 180,000 plus 26,400 times X. Double check that real quick. Let's see. That should be about right. Let me double check here. All right, so 15,000. Oops. Times 12 gives us 180,000. Then 15,000 times 2X. Minus 300. Oops. Uh-oh. That should be about right. 2X is 30,000. Oh. What's going on with my calculator? That's the problem. Yeah, 26,400. And then minus 600x squared. All right, so let's see here. All right, so we got a revenue function. We're taking our quantity or our price function times our quantity function. But now we got to define our cost function. And cost function here is going to be defined as the unit cost per unit, or the price per unit to make the cost per unit, also known as the unit cost, multiply by the quantity, how many cars we're going to be making. All right, to figure our total cost, we got to first figure out how much it's going to cost us per unit, and then multiply that by how many units we plan to produce. That's the unit cost times quantity. Well, what does it tell us here? It tells us in the information above that it costs $12,000 to produce each car. So our cost function, the unit cost is $12,000 here. Oops, come on. We're going to multiply this by how many cars we're going to make, which is being represented by what? Our quantity function, Q of X. So 12,000 times Q of X. Where Q of X we defined as 12 plus 2 times X. All right, so in other words, the cost function is represented by the unit cost multiplied by the quantity function Q of X. So times 12 plus 2 times X, which gives us a cost function of 12 times 144,000 plus 24,000 X. Okay, so now we have our derivative function. Now we have our cost function. So now we can finally formulate our profit function. And again, how do we define profit? How do we define the profit function? As our revenue minus our cost function, P of X or R of X minus C of X. All right, so you're going to take our revenue, which was 180,000 plus 26,400. X minus 600x squared minus our cost function here, which is 144,000 plus 24,000 X. All right, to give us a profit function of, what would that be? 144,000 to give us, I'll put in terms of order here. So negative 600x squared plus 2400x. Oops, let's do 2400x. 2400x actually plus 36,000. Okay. So that's our profit function. In other words, that's the function that we're trying to optimize. We want to maximize the profit. Okay, so now that we have a profit function, how do we optimize it? How do we maximize and minimize the function again? By now finding its derivative. Okay, so now the next step is to find the derivative of this function. So P prime of X. All right, so let's see, what will be the derivative here? There is negative 600x squared. It's going to be negative 1200x or negative 1200x plus 2400, right? Derivative negative 600x squared is just negative 1200x. Derivative 2400x is just 2400. Okay, and now we set it equal to 0. So we're trying to find a critical value that will optimize this function. We're trying to find its optimal point. So now we set equal to 0 and solve for x. And solving for x using algebra gives us negative 2400 divided by negative 1200 gives us 2. Meaning what? That if we want to maximize our profit, we should make 2 price reductions. Okay, so we should make 2 price reductions if we want to maximize the profit that we make from selling these cars per day. But we're not just finished yet. We're not finished just yet. We're not just finding the optimal point for X, but also we want to define at this optimal point, at this critical value, what's going to be our price and quantity. And how do we do that? By taking 2 and plug it into the original equations for the price and quantity function. All right, so first, let's find the amount of quantity cars we're going to be making at 2 price reductions. So I'm going to take 2, plug it into 12 times 2x. So Q of 2 is going to be 12 plus 2 times 2 to give us 16 here. Okay, so this is telling us that we can produce and sell 16 cars if the price of each car is at, well, how do we figure that out? How do we figure out what the price should be of each car if we want to produce and sell 16? By plugging 2 into our price function. So now we're going to take 2 and plug it into P of X here. So we're going to evaluate our price function at 2. So P of 2. Our price function was 15,000 minus 300 times X, where X in this case will be 2. So 50,000 minus 300 times 2 gives us a price of 14,400. Okay. So 14,400, meaning if we want to maximize our profit, we should set our cars at $14,400 each, which can allow us to sell 16 cars per day to give us a maximum profit. What will be our maximum profit? How do we find our maximum profit here? By plugging 2, this critical value that we found, into our profit function. All right, so if we plug in 2 into the profit function, P of 2, all right, so negative 600 times 2 squared plus 2,400 times 2 plus 36,000 gives us a maximum profit here of $38,400 per day. Okay. So to maximize our profit, we should make 2 price reductions, which means we're going to set our price of each car at $14,400 each, which is going to allow us to sell 16 cars per day to give us a maximum profit of $38,400 per day. All right. So here we had to do a bit of work here. We first had to define our price function, our quantity function in terms of the number of reductions we're going to be making to the original price of each car. And then we had to utilize those 2 functions as well to formulate our revenue and cost function, because we want to try to figure out how to maximize our profit. And to know our profit function, we have to know the revenue and costs. So our revenue function was found by taking our price function times our quantity function. The cost function was found by taking our cost per unit times our quantity function. So the unit cost times Q of X. Utilize the equation for the profit function, which is defined as revenue minus cost. And since we're trying to optimize the profit, we had to find its derivative, set equal to 0, and solve for our critical value of X, where X is representing how many price reductions to make, which in our case wound up being 2. But again, Reading carefully exactly what we want from the problem. We want to find the quantity, the optimal quantity and optimal price. Meaning after we find our critical value, we have to plug it back into our quantity and price function, which in this case wound up being $14,400 per car, the price of each car, which allows us to sell 16 cars per day, which gives a maximum profit of $38,400 per day. All right, so let me pause this video and do two more examples in the next part.